media rumors about the Yellowstone volcano on the verge of eruption.
Bring an eruption from the Black Diamond Pool at Yellowstone National Park.
Here's the footage released by the USGS. It shows the eruption blasting out of a thermal pool, sending water several feet into the air.
A sudden and unsettling change rippled across the northern edge of Yellowstone National Park when scientists reported that a section of the ground had split open, leaving behind a jagged, gaping crack stretching more than 100 feet. It wasn't the product of a simple landslide or a random fissure caused by rain or erosion. This was something deeper, an event that immediately caught the attention of geologists, volcanologists, and seismologists around the world. The crack wasn't just a surface scar, it was a message from the restless forces that have shaped Yellowstone for hundreds of thousands of years. The ground in this region has always been alive, breathing through geysers, bubbling through hot springs, and shaking with subtle tremors. Yet, this fracture was different. It represented a tangible shift, a visible sign that the vast geological engine beneath Yellowstone had stirred once again. Before we start, hit the like and subscribe buttons for more exclusive news. The split appeared in a remote but closely monitored area near the park's western edge, where geothermal activity and uplift have been slowly reshaping the terrain for decades. At first glance, rangers believed it to be a simple surface fissure caused by recent rain and ground saturation. But closer inspection told another story. The crack was too clean, too linear, and extended too far to be dismissed as a simple landslide or surface movement. Scientists arriving on site quickly realized that the fissure marked a zone of stress release, an indication that the crust was adjusting to powerful internal forces building below. In a place like Yellowstone, such adjustments are rarely meaningless. The entire park sits atop one of the largest volcanic systems on Earth, a colossal caldera that last erupted about 640,000 years ago. While that may sound like ancient history, the caldera's behavior today still mirrors the same restless cycle of heating, pressurizing, and shifting that it has always followed. The splitting ground therefore instantly raised questions about whether new magma was moving beneath the surface, or if the crust was responding to a change in hydrothermal pressure. The smell of sulfur lingered faintly in the air as researchers examined the fissure, and subtle warmth radiated from the newly exposed soil, signs that thermal fluids might have been circulating closer to the surface than before. As word of the event spread, it became clear that this was not a minor occurrence. Ground-splitting events of this magnitude are exceedingly rare in Yellowstone, especially ones occurring suddenly and with such length. The fissure ran across a hillside dotted with lodgepole pines, slicing through the earth like a wound that had been waiting to open. Trees stood at odd angles, some leaning into the void as if drawn toward the newly formed chasm. Soil samples taken from around the site showed an increase in volatile gas emissions, particularly carbon dioxide and sulfur dioxide, both typical indicators of subsurface volcanic or hydrothermal agitation. Scientists quickly deployed a suite of monitoring instruments around the area. Tilt meters to detect subtle ground deformation, seismographs to record micro tremors, and gas analyzers to measure emissions in real time. Each instrument fed into a network connected to the Yellowstone Volcano Observatory, where teams of specialists began parsing the incoming data with intense focus. Initial readings showed that seismic activity had indeed spiked slightly in the days preceding the event. A cluster of small earthquakes, most too weak to be felt, had rippled through the region just before the ground gave way. The pattern suggested that the crack was the surface expression of a deeper stress redistribution within the crust, possibly triggered by the migration of fluids or even magma through fractured rock layers. What truly unnerved scientists was the fact that the ground had split without any major earthquake preceding it. Normally, surface ruptures of this scale accompany noticeable tremors, but this one seemed to have opened almost silently. Such a quiet rupture implied a slow, creeping process rather than a sudden jolt, the kind that points to the slow inflation or deflation of underground chambers. If the ground was rising, it could indicate that magma or hot fluids were pushing upward. If it was sinking, that might mean a chamber below had depressurized. Either scenario carried deep implications for the stability of Yellowstone's volcanic system. For decades, scientists have known that Yellowstone breathes. Its vast caldera rises and falls in rhythmic cycles that can span years or even decades. These cycles are caused by the ebb and flow of magma and hydrothermal fluids beneath the park's surface. The new crack might therefore represent a localized manifestation of one of these breathing phases, but on a more concentrated and alarming scale. Satellite radar images taken in the days following the event confirmed that the terrain around the fissure had undergone measurable uplift. Just a few centimeters, but enough to mark significant underground movement. The atmosphere among the research teams was tense but focused. Geologists compared notes, mapping the precise coordinates of the fissure and tracing its orientation relative to known fault lines. It appeared to align roughly with a system of older fractures that cut across Yellowstone's western boundary, a region already known for periodic seismic activity. These older faults act as weak zones within the crust, places where stress can accumulate and then release in abrupt ways. The reactivation of one of these zones, especially near geothermal hotspots, suggested that something beneath the park was reconfiguring. Every expert understood that the forces at play were immense. Beneath Yellowstone's serene landscapes, its forests, meadows, and glittering lakes, lies a magma chamber stretching roughly 50 miles long and 12 miles deep. Above that chamber, a smaller, shallower zone of molten and semi-molten rock feeds the park's famous geysers and hot springs. When gases and heat from these molten reservoirs escape upward, they interact with groundwater, creating the thermal marvels that millions of visitors see each year. The newly formed crack might have opened a pathway for these gases and fluids to rise, altering the delicate balance of pressure that drives Yellowstone's geothermal features. Indeed, in the days after the fissure appeared, park rangers reported subtle changes in several nearby hot springs. Temperatures fluctuated, colors deepened, and some geysers released thicker plumes of steam than usual. None of these changes were catastrophic, but they reinforced the idea that the underground plumbing of the park had shifted. Scientists took this as a natural laboratory moment, a chance to observe in real time how a geological system of this magnitude adjusts to internal stress. The implications of the event reached beyond the scientific community. For local residents living in the surrounding regions of Wyoming, Montana, and Idaho, any sign of unusual activity in Yellowstone evokes deep unease. The area's volcanic history looms large in public imagination, often associated with the notion of a supervolcano capable of global-scale eruptions. While scientists repeatedly emphasize that no eruption is imminent, a visible crack stretching 100 feet across the ground inevitably triggers anxiety. The media, as always, amplified the drama, with headlines suggesting everything from apocalyptic eruptions to sudden geological collapse. Yet, for those working on site, the focus remained on understanding the mechanics of what had occurred rather than speculating about worst-case scenarios. The split ground offered a rare glimpse into the dynamics of Yellowstone's restless interior. Geophysicists analyzing the event pointed out that such fractures often act as safety valves, releasing pressure before it can build to dangerous levels. In that sense, the crack could be a sign of the system relieving tension rather than accumulating it. Still, even a harmless release has cascading effects. It can alter groundwater flow, change gas venting patterns, and potentially create new surface hazards. For example, if hydrothermal fluids find new pathways to the surface, they could create new hot springs or even small steam explosions, events that have occurred before in Yellowstone's history. The surrounding terrain also presented challenges. The fissure cut through a slope composed of loosely compacted volcanic ash and pumice, materials that are prone to erosion and further collapse. Geotechnical teams installed stakes and laser sensors to track any widening or deepening of the crack, aware that the ground could continue shifting for weeks. Early readings showed minute daily variations, as if the Earth was breathing in slow, uneven pulses. These oscillations hinted that pressure changes below were ongoing. Scientists compared the data with previous episodes of ground movement in Yellowstone, including the 2014 episode of Uplift near Norris Geyser Basin and the 2018 sequence of small quakes. Both past events had involved subtle crustal deformation tied to hydrothermal or magmatic processes, but none had produced such a visible, elongated fissure. The uniqueness of the 100-foot crack lay not only in its size, but in the context of Yellowstone's broader geological activity. Over the past few years, satellite data had already shown a gradual increase in ground uplift across portions of the park, suggesting long-term pressurization of subsurface reservoirs. The new fissure, therefore, might represent the surface manifestation of years of cumulative strain, reaching a critical threshold. In a sense, the crack became a geological diary entry, a single physical sentence written by the forces of the Earth's mantle. Every layer of rock it exposed told a story of ancient eruptions, of ash deposits compacted over millennia, and of relentless heat churning below. Standing beside it, researchers felt the immensity of geological time compressed into one moment. The air shimmered faintly with heat, and faint wisps of steam curled upward from parts of the fissure's edges. Instruments placed nearby recorded subtle temperature gradients, suggesting that geothermal fluids were indeed moving closer to the surface than before. The scientific community approached the event not only as a potential warning sign, but as an opportunity to refine their models of Yellowstone's internal structure. Ground-splitting events provide critical clues about the movement of magma and fluids within the crust. By analyzing the orientation and depth of the crack, scientists could infer the direction of stress fields and the behavior of fault systems that lie invisible beneath the surface. Using ground-penetrating radar and magnetotelluric imaging, they began mapping the subsurface conductivity to identify potential fluid-filled zones. Early models suggested that the fissure might sit above a pocket of hydrothermal pressurization, essentially a trapped zone where hot water and gases had built up until the overlying rock finally gave way. Such pockets are not uncommon in Yellowstone, but when they rupture, they can set off a chain reaction of pressure adjustments throughout the surrounding crust. As these adjustments propagate, they can trigger minor earthquakes, shifts in geyser activity, and surface deformation miles away from the initial event. The park's interconnected geothermal system acts like a living organism, with pressure pulses traveling through its network of conduits and fractures. A single rupture, even a small one, can ripple through this network, altering its behavior in subtle but measurable ways. The notion that the crack could be a surface symptom of deeper magmatic movement also couldn't be dismissed. While direct evidence of magma ascent is difficult to obtain, certain signals, like specific gas ratios or patterns of uplift, can hint at its presence. Scientists began testing gas samples collected near the fissure, focusing on the ratio of helium isotopes. Elevated levels of helium-3, a rare isotope associated with mantle-derived magma, can signal that molten material is moving upward. Preliminary results hinted at a slight uptick in helium-3 concentrations, though far from levels that would suggest an imminent eruption. Still, the readings added another layer of intrigue, implying that something deep within Yellowstone's plumbing system was indeed shifting. Even the most seasoned scientists couldn't help but feel a sense of awe mixed with unease. Yellowstone is one of the most studied volcanic systems on the planet, yet it continues to surprise experts with its complexity. The split in the ground, stark and silent, became a reminder that despite all the technology, all the sensors and satellite data, the Earth retains mysteries that cannot be fully predicted. Human understanding, no matter how advanced, still stands in the shadow of geological power that operates on scales far beyond daily comprehension. Over the following weeks, researchers continued their meticulous work. Drone surveys provided high-resolution imagery of the fissure, revealing patterns invisible from the ground. The crack widened slightly in some areas, though not catastrophically. Nearby, small vents began to emit faint plumes of steam, and patches of vegetation turned pale yellow, scorched by heat or exposure to gas emissions. These subtle transformations painted a portrait of an ecosystem adjusting to the Earth's shifting breath. For those studying Yellowstone's deep-time history, the event also offered a sobering parallel to the processes that have shaped the region over millions of years. Long before humans walked the planet, this landscape had been torn apart and remade countless times by eruptions, subsidence, and uplift. Each fracture, each geyser vent, each mineral-stained terrace stands as a reminder of the tension between creation and destruction that defines the park's existence. The 100-foot crack was simply the latest punctuation mark in that story, but for those who witnessed it, the immediacy of the moment, the sound of cracking earth, the smell of sulfur, the shimmer of heat, felt profoundly real. The scientific implications extended beyond Yellowstone itself. Understanding how the crust behaves in such a supervolcanic setting informs models used to assess other volcanic systems around the world. From Iceland's rift zones to Japan's calderas, the same principles apply. Stress accumulates, fluids migrate, pressure builds, and eventually, the ground responds. Yellowstone serves as a natural laboratory for studying these dynamics, and every event, even one as localized as a fissure, enriches that global understanding. Teams from multiple research institutions collaborated on interpreting the data. They compared Yellowstone's crack event with similar occurrences in other geothermal regions, such as Long Valley Caldera in California and Taupo in New Zealand. In those regions, ground fissures had sometimes preceded hydrothermal eruptions or changes in geothermal discharge. The consensus forming among experts was that Yellowstone's fissure likely represented a stage in that same continuum, a physical manifestation of pressure redistribution within the park's intricate geothermal network. The intensity of interest surrounding the crack also reignited public curiosity about the hidden processes that sustain Yellowstone's beauty. Visitors gazing at Old Faithful or the Grand Prismatic Spring often marvel at their splendor without realizing that these wonders exist because of the same heat and pressure that now seem to be cracking the ground open elsewhere. The delicate balance between surface tranquility and subterranean turmoil defines Yellowstone's identity. It is a place where beauty and danger coexist, each dependent on the other. As more data flowed in, scientists noted that the ground around the fissure emitted low-frequency tremors, subtle vibrations known as harmonic tremors. These tremors are particularly interesting because they often indicate fluid movement through rock fractures. Unlike sharp earthquake jolts, harmonic tremors resonate continuously, as if the earth itself were humming. The tremors detected beneath the fissure suggested that hot water or gas was migrating upward, possibly using the crack as a new conduit. If confirmed, this would mean the fissure had transformed from a mere break in the ground into an active venting pathway, altering the landscape's thermal regime. At night, thermal cameras captured faint glows along portions of the crack, invisible to the naked eye but detectable as infrared emissions. The warmth hinted at subsurface heat exchange, another sign of fluid circulation. While not dangerous in itself, this process underscored how dynamic and sensitive Yellowstone's crust truly is. It reacts quickly to shifts in heat or pressure, adjusting through movement, fracture, or flow. The fissure was both a symptom and a signal, an open wound through which the Earth communicated its inner state. Amid this scientific fascination, there was also a palpable sense of respect, an acknowledgement that Yellowstone's vast system operates on timescales and forces beyond human control. Every expert who walked the site knew that they were standing atop a living giant, one that slumbered but never slept. The crack was a whisper from that giant, a reminder that beneath the calm of forests and meadows, immense power waits in silence. By the end of the monitoring phase, the fissure had stabilized. Its edges hardened under the sun, and dust settled into its crevices, yet the story it told would ripple through geological studies for years. Researchers compiled data into models that would refine hazard assessments, improve prediction tools, and deepen understanding of crustal behavior in volcanic regions. The event reaffirmed that Yellowstone remains one of the most dynamic and unpredictable natural systems on Earth. The split ground was not a disaster, but a revelation. It revealed that the park's volcanic heart continues to pulse with vitality. The forces that created Yellowstone are still at work, shaping, adjusting, and reminding humanity of its smallness before the grandeur of geological power. For all the sensors and satellites, there remains something profoundly humbling about standing before a 100-foot crack in the earth and realizing that it appeared not through violence, but through the quiet persistence of natural energy seeking release. The fissure now stands as both a scientific landmark and a natural testament to Yellowstone's living geology. It underscores that the Earth is never truly still, even in the places we call stable. Beneath the surface, immense reservoirs of heat and pressure continue their timeless dance, sometimes revealing themselves in fleeting moments like this one. A split in the ground, a subtle tremor, a whisper from the deep. Each event adds a line to the story of a planet that even after billions of years remains profoundly alive. And so, the crack in Yellowstone's ground stretching 100 feet across and carved by unseen forces, becomes more than a geological curiosity. It is a reminder of the intricate, unseen workings of the planet we inhabit. The earth beneath Yellowstone is ancient and wise, communicating not in words but in fractures, in steam, and in tremors. Those who study it listen carefully, knowing that every fissure, every shift, every pulse is part of a greater pattern, an ongoing dialogue between the surface world and the fiery depths below. The splitting of Yellowstone's ground, while alarming, was also enlightening, a vivid display of the balance that sustains one of the most remarkable landscapes on Earth. It is the raw conversation of stone and heat, of pressure and release, echoing through time, reminding all who witness it that this planet is still writing its story one crack at a time. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on Yellowstone's ground splitting open recently? We want to hear from you. Thank you for watching and see you next time.